Hello everyone, my name is Kapil Sethi. I work at Samsung Semiconductor, and the topic for presentation is integrating composable memory systems into storage intensive workloads. So as you can see from the list here, many folks from different companies work on this. Uh, Today, Seema from Ampere, Ravi from Micron, and myself will do the presentation. Okay, so we'll go through first of all what is the motivation and background for this work, why we are doing this, and then we'll look at some of the results of composable memory systems, specifically CXL memory on storage and memory intensive workloads, right? Redis or Apache Cassandra or Apache Spark. And then we'll look at next steps and call to action. Okay, so when we started working on evaluation of workloads using composable memory systems or CXL memory, we realized that there are different types of workloads and they might fall into different categories. They could be compute bound or memory bound, and within memory bound as well, they could be constrained by memory latency or memory bandwidth. Now, following the charter of CMS, we are focusing on two different aspects. One is native memory expansion, where our goal is to maximize performance over dollars. And on the other side of the spectrum is a pooling solution. And there the goal is to lower dollars per gigabyte. So having said that, in presentation right now, we'll cover two different aspects, two types of workloads. One is the online storage and other is data analytics. And as you can see here, there are different workloads we are exploring and you're gonna hear them from different presentation throughout the day. Okay, so first of all, Redis on CXL devices. As an overview, what is Redis? A lot of us know it's a quick access database where data is stored in memory instead of your traditional SSDs or disks. Because the data is stored in memory, so the performance depends on the memory capacity and memory latency. And what are the typical use cases of a Redis database when you need quick response data access, data caching, vector database, etc. Other challenge that we see with Redis database is about right-sizing the Redis cluster. So one of the issues that we hear from people who work on it is the problem of over-provisioning the memory, which often leads to memory stranding, where all the computes are being used, but there is a memory that is left behind stranded. And we can use CMS solutions to solve these problems. So we can have a situation where Redis instances in a cluster can be shared with a memory appliance or a shared memory across different Redis instances. So that could help to allocate memory on per need basis. And when there is not enough need, memory can be released to other rack level applications. But before we go to pooling, we have to do the first step, and the first step is memory expansion. And we need to find out, is CXL memory even suited for handling Redis queries? What are the performance impact? How does CXL memory compares to your native DIMM memory for Redis application? So we worked on it. We worked on assessing the performance impact of CXL memory for Redis. So as you can see here on the picture on the left side, we have one setup where the Redis is running on CXL memory only. So you have two 256 gigabyte CXL modules. And on the other side, you have Redis running on DRAM, main memory only, which is your native DIMM slots. Again, the capacity is the same, 512 gigabyte on both sides. And we want to see how the performance compares between these two setups. So having established that baseline, now let's look at results. So these are initial results where we compare the latency, which is the P99 latency, the tail latency, and operations per second between Redis, running Redis on CXL or native DIMMs. The results are very promising considering that a lot of optimization can be done further through software and through improved hardware as well. So we feel we are on the right track in this. And these results will only get better over time. So having said that, what are the next steps? What are we going to do? As I said, the results are promising from native expansion testing on Redis. Next step is to move it ahead. Go to multi-node, CMS pooling solution evaluation, and also do a TCO model evaluation from the business point of view. So this was about Redis. Now let me pass the mic to Ravi, who's going to talk about Apache Cassandra.
Thank you, Kapil. Hi, everyone. My name is Ravi Gummaluri. I'm part of system architecture for Micron. Today I'm going to talk about Cassandra, Apache Cassandra workload analysis that we have done on with respect to the local DRAM versus the CXL. How is the scaling happening, and what are the advantages we are seeing, and how is Cassandra workload when moved to the CXL, how it is performing. So we have some analysis. Given the time what we have here, probably we'll not be able to cover all the analysis. A white paper, we are planning to publish a white paper with detailed analysis that will help out to understand the workload better. Today I'll just give you an overview and what results we are seeing for the first instance, what we are seeing. But a white paper with the detailed analysis is going to come out that will be helpful for you. Okay, just an overview of what is Apache Cassandra. Apache Cassandra is an open source distributed NoSQL database. It is built for scalability and fault tolerance. Some of the typical use cases are like your social media platforms, real-time data analytics, e-commerce, fraud detection, and risk management. Very popular ones were like, the Twitter, Instagram, Netflix. They all use Cassandra workloads. Cassandra database. When coming to the scalability and fault tolerance, scalability is like the number of nodes that you can add to the cluster because of the increased workload. That is all about the scalability. But for scalability, you need sufficient memory and a high-performing SSDs, and your network link also should be good enough. For the fault tolerance, you need to do a data replication. So that all also needs more memory, more capacity. So for scalability and tolerance, definitely we need sufficient memory, which is what we are talking about in the CXL. Just quick overview on the single node architecture here. It's not completely calling out what is Cassandra architecture here. We are trying to call out how are the read and write operations are happening in the Cassandra and how the flow is happening. In a single node, if you see in the DRAM, the mem tables are actually sitting in where you call it as a data cache, and you have a commit log for the persistence reasons, and you have SSD tables for the increasing your capacity or the data sets. When you do a write, basically, the first step is it basically goes into the commit log, and you can recover it if you do it in a commit log, which is sitting inside the SSD. In the DRAM, you have mem tables, and the write goes and writes into the mem table. In the read sections, you can see that first it goes and checks in the cache, which is mem table. If you can find a data there, you can get it data from there. If not, you have to do some more calculations and get it from the SSD tables, which is sitting inside the SSD. Periodically, these mem tables are flushed to the SS tables because for the persistence reasons. And the memory is limited in DRAM. You cannot cache every data sets inside your memory table. So SS tables have the complete data set here. Some of the analysis that we did with CXL versus the local DRAM, the basic setup that what we are trying to demonstrate here is, on the right-hand side is the basic DRAM. We have used a Cassandra client, which is, we used a tool called Cassandra Stress Test, which is the Cassandra client here, sitting in a client's environment. And we have a server, which is connected, client and server is connected with 100 gig Ethernet here. And we have local DRAM here with 8 channels with 64 gig RDIMMs connected to it, which is around 512 GB of capacity. And we have 3 1 TB SSDs, which the dataset sits in for the commit logs and the data SS tables. When we run the Cassandra stress test here, basically targeting only DRAM, we saw some analysis, the numbers here, and when we run the same Cassandra client targeting the CXL memory, we have some results. We are going to talk about it. But if you see here, the infrastructure, what we have is CXL is half the bandwidth of the local DRAM, and the capacity is almost double here. And the latencies, we all know the CXL has a higher latency than local. So basically, we are targeting whether this workload is sensitive to latency or memory or capacity that we are trying to analyze here. The bandwidth is half and the latency is high. Only thing what we are trying to play around is the capacity here, having more capacity with CXL here. Some of the initial results that what we have seen here is, if you see CXL is performing at par, at lower data sets, the CXL and the DRAM is performing similarly. The K-ops are basically same. When we increase the data set where it is beyond the capacity of the local, where CXL can fit in, but DRAM cannot fit in, that's where you can see CXL K-ops are better than the local DRAM. With respect to the latency, it is almost par there. There are various scenarios that we have taken, the 2:1, 1:1, and 3:2, various read-write ratios that we have analyzed here. The outcome was like, the bandwidth and latency are not really affecting the K-ops, which is the output. What we observed is the CXL is performing par with the local DRAM. In some cases, with the CXL additional capacity, it is performing better than the local DRAM. So these are some of the initial analysis. If we see the summary of the analysis with single node, the results are really promising. And what we can infer is like the Cassandra is insensitive to latency and bandwidth because we are running the workload with half the bandwidth and higher latency, but still the K-ops are performing better or par with local DRAM. So the other analysis that we are trying to do is, can we scale this to multiple nodes? Because multiple nodes requires more capacity. That's where probably the local DRAM might not be performing well. With additional capacity, what we are adding with CXL, probably scaling will be far better, and the results has to be analyzed further. Those are the next steps. And the TCO model that can play with CXL, because if the second tier is good enough for the Cassandra workload to move to the CXL, then we can have a TCO play around it. So we are analyzing the TCO model as the next steps here. Having said that, I'll pass on to Seema, who will be talking about Apache Spark.
Good morning, everyone. I'm Seema Mehta at Ampere Computing in Technical Marketing. I'll be presenting on the Spark analysis here. So as we know that processor core counts have been increasing, and that's driving the memory capacity and memory bandwidth demands. And that's especially true for memory-intensive workloads like Spark and Presto, because they are the analytics engine for doing the in-memory processing and caching operations and shuffle operations. The traditional servers have a limited memory capacity, and so if the data sets are more complex or the querying performances are more severe, then that can lead to more I/O activities and paging demands. So that's why this is where the Composable Memory Solutions can help. And then there are, of course, two scenarios, native memory expansion and memory pooling. So the two use cases that are being discussed here, one is batch processing and one is real-time processing. So in a distributed computing environment where there could be uneven Spark tasks, it leads to memory stranding because the memory utilization by each node in a cluster varies from time to time. And therefore, because it varies, then it can cause data spill or memory stranding. In addition, there is also the network-based data transfer overhead that can lead to data duplication. In case of, and that causes the memory footprint growth. In case of real-time processing, since Spark is a memory-bound workload, and the latency spikes can also force new node deployments, which further increases the TCO. And so the goal here is also to lower the TCO, or the total cost of operations. The existing work that focuses on memory expansion for Spark has been already discussed via memory tiering, and that has shown to improve the performance speed up by almost 2.5, 2.6x versus simply DRAM. But the memory stranding remains unaddressed. So that's what the focus of my work here is going to be. So the proposed solution is memory pooling for Spark in case of batch processing. Because batch processing, we are assuming that it's not so latency sensitive. So it's relatively latency insensitive versus a real-time processing. And what happens is that when you're pooling memory from different nodes into a combined pool, then you're minimizing the memory stranding, you're minimizing data spill, the data transfer overhead, and the data duplication. All these effects are getting minimized. So in that sense, it would improve the TCO because there's no stranded memory now, or it's mitigated. And when you do a compressed CXL tier, which means the data is being compressed over the CXL interconnect, that would further lower the TCO. Some back of the envelope calculations in two scenarios, without pooling and with pooling. So when you have the near CPU socket memory, assuming 200K for the total memory cost in both cases, without pooling and with pooling. So you have the poolable memory again at the same amount, 200K, but with the 20% CXL premium, let's say it's now 240K with pooling. But because we are removing the stranded memory, or we are minimizing and mitigating it, we are saying that with pooling, the stranded memory could go down to as low as 0. And so with power absorptions roughly about 60K and 40K in two scenarios, the total cost comes out, and we see that there are almost 30% TCO savings at the higher end with pooling, and which is pretty impressive. And again, like I said, with the TCO savings with CXL, and then further TCO savings with compressed CXL tier. So the next steps here and the call to action would be to analyze the memory usage patterns and to estimate the memory that can be pooled, and then design and test the reference architecture, do TCO analysis for composable memory systems, performance benchmarking for compressed CXL tier, and then call to action is, we have written a white paper, and so download that paper, download the TCO calculators, reference configurations, and then provide feedback and collaborate to improve these reference configurations and TCO models. And of course, join and contribute to the OCP CMS working group. And then the QR code to scan is shown here on the right-hand side.
Can she stay for one question?
So Reddy is saying there is no time. So you have any questions you can take.